everybody. These are going to be section 3.3 class notes examples. So first, we're going to translate each of the following statement into a symbolic form. We're going to consider D the set of all people, and L of xy be the predicate that means x loves y. So if we want to write everybody loves somebody, then we want to make sure that we start with that for all x that belongs to the set of people. So for all x that belongs to D, then because everybody loves somebody, then it's gonna exist somebody in this set of people, so that L of xy. Now, if I want to say somebody loves everybody, is the opposite. I say it says somebody that belongs to the domain of people, so that for all y that belongs to the set of people, then that someone is going to love everyone. So it's going to exist x that loves everyone in the sets. Now, for everybody loves everybody will be for all x that belongs to D, and for all y that belongs to D, then L of xy. Now, last, somebody loves somebody will be the opposite. It will be assist y that belongs to D, so that assist x, sorry, that belongs to D, and assist y that belongs to D, so that L of x, y. So that'll cover pretty much all the options. Now, let's go to question number 2. And we want to translate the following into English. It says here, for all x in the real numbers, it says another real number and another real number y, so that the sum is 0. Also, for B, now we're saying there is a real number, or there is a real number y for all real numbers, so that the sum is x. And in particular, this also can be said there is a real number such that for all real numbers, adding it to any real number gives that real number back. In particular, that real number y that we're finding here is y is equals 0. Since y equals 0 plus any x is just going to give me the x back. C, we have that for all x that belongs to R, and for all y that belongs to R, x plus y is equals y plus x. So that means for all real numbers, xy, the sum is commutative. This is the property of the real numbers that we're kind of pointing here, and is that the sum, the order in the sum is not going to matter. Okay, so for all real numbers x and y, their sum is commutative. Okay, all right, so let's move to question number 3. We want to determine the truth value of each statement. So in here, we just want to know if this true, is this false, what is going on with this. Here it says for all x that belongs to R, this is a y that belongs to R, so that the sum is 0. So this is saying that this is an opposite number. In particular, that's opposite number is going to be y equals minus x for any real number x. So yeah, this is true. For B, we have, this is a number y for all real numbers so that the x times y is equal to 0. But this is false. Wait, no. Yeah, this is okay. Yeah, it's just a y for all real numbers. In particular, if y is equal to 0, then x times y is going to be 0 regardless of what number that is. So yeah, this is fine. This is true. Now, C, for all x that belongs to the integers now, this is another integer so that x plus y is bigger than 0. And this is actually false. As a counterexample, you can pick x equals 0, which isn't the real number, is in the integers. X equals 0 belongs to the integers. And it says for all y, x plus y is equal to 0, but let's pick y is equal to 1. Well, you can see that x times y is not going to be 0. It's actually going to be, it's not going to be bigger than 0. It's actually going to be 0. So that's not bigger than 0. So it's false. For D, it says x that belongs to the integers, and it says y that belongs to the integers, so that x plus y is equals 10. And that is actually true. So this is saying that it says two numbers so that the addition is 10. In particular, we can pick x and y equals 5, and x plus y is going to be equals 10. There's a bunch of more. You can go with 9 and 1, 8 and 2. So there's plenty of examples that prove this true. Write the negation of each of the following statements. So here for question number 4, remember that when we're doing negation, we start by negating in order. So the negation of this for all is an assist. It says x that belongs to R. Then the next is another for all, so we're going to negate with an excess. This is y that belongs to R. And then last, we negate the property. If x plus y bigger than 0, the negation of that will be x plus y less or equal than 0. This will be the negation of this. Now for the negation in B, we'll start with a for all. So we transition to an SS. This is x that belongs to R. Then second, we have an SS. So the negation is going to be a for all, y that belongs to R. And then finally, we negate the property. So we say such that x times y is different from 1. Last, it says x that belongs to C for all y that belongs to C, so that x plus y equals y. So if I'm going to negate that, let's start with for all x that belongs to C, negating the assist. Then I negate the for all with an assist y that belongs to C, and then x plus y different from y. That'll be the negation in this. Now, question number 5, we want to write the negation in symbolic form and then translate to English. So it says for all students, this is a course C such that S is enrolled in C. And so the negation for this is assist a student S for all course C such that S is not enrolled in C. Which in English, this will mean there's going to assist a student that is not enrolled in all courses. Okay, so the original was for all students. There's gonna be a course where they are enrolled, but the negation of that is that's gonna assist a student that is not enrolled in all courses. Okay. Now, let's move on to the next one. So we have assistant professor P such that for all students, the professor has taught the student. So the negation of that will be for all Professor P assisting a student right? So we're negating the for all assisting a student, and then so that P has not taught S. And so the translation to English of this will be every professor has at least a student they have not taught. Every professor has at least one student they have not taught. Okay. All right. Moving on. Question number 6. We have consider for all x that belongs to R, assist a y that belongs to R so that x is less than y. So this is saying that for all real numbers, assist a real number that is bigger than all of them. And this is actually false. Wait. No. For all real numbers, assist a real number that is bigger than that particular real number. Okay. It's not that it's bigger than all real numbers. It's just that it's bigger than that particular real number. So given I have x, so given x, I have y equals x plus 1, and that's going to be bigger than x. Okay? So this is actually true. Now, the negation of this in symbolic form will be assist an x that belongs to R for all y that belongs to R, so that x is less, is bigger or equal than y. Okay. Is the negation true? No, it's going to be false because the original statement is true. So it kind of makes sense that this is going to be false. And if you think about it, this is saying that it's just a real number that is going to be bigger than all real numbers. Now this was what I was thinking initially. It's saying, is this a real number that for all the real numbers, x is bigger than that real number? And this cannot happen because you're always going to find one number that is bigger. So it's impossible to have that for all numbers. Now, and in particular, like let's say you pick 5. 5 is going to be bigger than 1, 2, 3, 4, but then it's going to be less than 6. Okay? You can all, given that you pick that number, you're always going to find a number that is bigger than that one. So this will never become true. Now, for question number 7, it says explain the difference between for all x that belongs to R, it says y that belongs to R, such that y is bigger than x, and it says y that belongs to R, such that for all x that belongs to R, y is bigger than x. And this is just precisely what we were discussing before. Here, what we're saying is, hey, for all the real numbers, there's always going to be one real number that is bigger. So this one is true. And we prove it with y is equals x plus 1. X plus 1 is always going to be bigger than x. In this one, this is saying, hey, there's going to be a real number that's bigger than all of them. And this can happen. This is false. Once that y is selected, then y plus 1 exists, right? And y is not bigger than y plus 1. And that's it. This is the way to prove that that is false. Now, last, let D be the set 1 to 3 and E equals 2, 4, and then consider the predicate P of xy, then x divides y. So we want to know is for all x that belongs to D, for all y that belongs to E, this is true. And we got to justify by checking all the cases. Okay? And so, for example, just doing a combination, P of 1, 2 will be 1 divides 2, which is true. Because this is saying in notation 1 divides 2 means that 2 is 1 times a number, which in particular is 2. So that one works. We can have P of 1, 4, which is 1 divides 4, or in notation 1 divides 4, which means that 4 is equals 1 times something, which is 4, so this works. However, and we got to check all the cases, of course. Then you can do P of 2, 4, and this says 2 divides 4. And this will be 2 divides 4, which actually works because 4 is 2 times 2, so that works too. Now, 2 divides 2 is trivial. 2 divides 2 is 2 equals 1, 2 times 1. 2 divides 2 is 2 divides 2, and is 2 can be represented as 2 by 1, which is fine. Now, the problem comes when you get to 3. P of 3 and 4 is something that's not going to happen because then 4 will have to be 3 times something, an integer. And that integer does not exist. And that x with x that belongs to the integer, so that 3 times x is 4, doesn't exist. And in the same way, P of 3 times 2 doesn't exist. There's no number, so that 3 times y is 2. So this is going to fail in here. Now, assist x that belongs to D for all y, so that P of xy is true. So we're looking for 1x in D, so that P of xy is true for all y. And we know them from this. Actually, x equals 1 works. X equals 2 actually works too. So this is true. Now, for C, says, for all x that belongs to D, exists 1y, so that P of xy is true. So we only need one of them for all of them. Okay? And this is false, because we don't have anything that 3 works. So P of 3, 4 doesn't work, and P of 3, 2 doesn't work. So there is no element in E that is going to help me make P of 3 that element true. So that's going to make it false. All right, so this is the end of part 1 of the examples for 3.3.